dispersion. Okay, and we said that the index refraction can, in fact, and it is, in most cases of any material, the index refraction as a function of wavelength is not a constant. It actually has a functional form. This is just an example. Okay, so in the case of glass, so glass has an index refraction that, it is larger for blue. This is red. So index refraction for blue is larger, as you can see. I'm just cooking up numbers, but these are just cooked up. So index refraction is different for different wavelengths. So it so happens that if you say this is glass and this is air, and suppose light is coming in, suppose this is white light, which is composed of all colors like the sunlight. And if you can bring it in at some angle theta in, because the index refraction of the blue wavelength is larger, it's going to bend more, and then the red will be bent less. And of course, every other color in between is there as well. There's the yellow and there's other colors in there. And so everything else will be there. But the extremums of the human vision system is pretty much blue on one end of the spectrum and the red in the other part of the spectrum. And so therefore, if the white light goes in at an angle into a medium like glass, you'll see a rainbow of colors because of this effect that the index refraction is different for different wavelengths. So they all have their own angle of refraction, which is different from the other ones due to the index refraction, due to the index being different for different wavelengths, which is the basis for rainbow effect in the sky when you have water droplets. So when you have water droplets, and you can model a water droplet with a spherical shape of water droplet, and when the sunlight hits it, it goes in and bends, of course, but it bends. The red, well, the red gets bent less, the blue gets bent more, and then of course, some of it leaks out, but we don't care about the leaking of these things. Okay, but there's an internal reflection also for each of these guys. And what happens is you see that the colors will separate from each other like so. And so you'll see, your eyes will see the color separation. You're somewhere on the ground and you're looking at this thing, and you'll see this rainbow effect in the sky due to this water droplet bending the light towards you. But because the index refraction is different for different wavelengths, you see the separation of the colors, just like the drawing on the left. When white light goes into glass, it separates into different colors. Okay. All right. Any questions? All right. Let me move on. So that was just the chromatic aberration effect, where colors separate due to the index being different for different wavelengths. Okay. Now let's go to total internal reflection. Okay. So this effect is actually pretty important. I'll tell you why in a second. All right, so suppose the source of light is here. In a medium, say this is N1 and this is N2. In a medium, that N2, N1 is larger than N2. So the examples are glass here and air here, because these are just examples. Okay. But this time the source of light is inside the glass instead of coming from outside into it, like usually we consider. So if the source of light is inside the glass, this is an example, but anytime you have an index larger than the outside and the light source is in the larger index, the situation is the same. So let's follow a ray of light that goes, a ray of light that just goes in like that. And if you remember the law of refraction, when the ray of light goes in from a higher index to a lower index, it goes towards the normal. It bends towards the normal. Okay. I should draw this with blue. Okay. So, I'm sorry. No, this is wrong. It goes away from it. I mean, I wrote. Let me recapture this thing. So coming in, N1 and N2. If N2 is larger than N1, it goes towards the normal. If N2 is less than N1, it goes away from the normal. Okay, we are going into it less dense, so we're going to go away from it. So this is what happens. Now, if you consider this ray, of course, if you follow a ray that goes directly up, nothing happens, it just goes through. Of course, some of it would get reflected, but there's no bending when it's normal. But whenever there's any other angle, it always goes away from the normal because we're going from a higher index to a lower index. Okay, so this is from higher index to a lower index. But look what happens at some point down the road here. Okay? At some point, you get to an angle where the ray of light finally goes parallel to the surface, where this angle becomes 90 degrees. Okay? So all of a sudden there is an angle, there is a ray that produces this angle 90 degrees when it comes out, which means it's going parallel to the surface. Now, this is a critical angle. Okay? Because if you go even beyond that, so if you go beyond this thing, guess what happens? The beam of light completely gets reflected internally. So beyond this point, the rays of light get reflected completely. Okay? So they just completely get reflected inside the high index material. All right, so we can actually go ahead and calculate that critical angle. Remember Snell's law? It was N1 sine of theta 1 equal N2 sine theta 2. So if we just go with the critical angle there, okay, let's say N1, and this is theta 1, and then this is theta 2. All right, so N1 sine of theta 1 is equal to N2 sine of 90 degrees. That's just Snell's law application at this exact point. All right? And that critical angle is in fact theta 1. And so what you get is theta critical becomes sine inverse of N2 over N1. Now, this is N2 being less than N1, by the way. We already know that. Okay, so this is your critical angle for beyond which, if it's larger than that, you get internal. So if theta is larger than the critical angle and equal to it, you get total internal reflection. All right, so what is this good for? What is this total? I mean, if this angle is this large or larger, the interface between these two materials with two indices acts like a complete mirror. It acts like a real mirror. So what is that good for? Here. Fiber optics. Okay, an optical fiber. Okay, works on this principle. So how does this work? Here we go. Here's an optical fiber. This is made out of glass. Okay? And it has a flat surface. Everything is glass. So a beam of light, say light goes in from here into this glass rod, so to speak. Okay? And of course, a local normal to that surface as soon as it gets in. So it bends in a little bit. By the time it reaches here on this wall, this angle with respect to the where it reaches on the wall is already larger than the critical angle we were just talking about. Okay? This angle is larger than the critical angle. And so that surface acts like a real mirror and you get a total internal reflection. So the beam then goes in like that. And of course, it keeps going and bounces off the other walls and so on and so forth. So it gets trapped inside this fiber. So you can see how you can send a beam of light, and you can then, on top of it, send a signal, meaning you turn it on and off in certain fashion. And an optical fiber then can be used as carrying optical signals from a transmitter to a receiver, which is how it all works on the principle internal total internal reflection. Okay. So this is a fiber. Of course, in reality, optical fibers are a little bit more complex, because an optical fiber that is just a piece of glass rod will be vulnerable to damages on the surface. So they actually, in reality, they put glass, and they have other system of jackets that go on top of this thing, and to protect it for protection. But then you have to be careful, because the index refraction of these protectants have to be less than glass. So the index of these guys need to be less than N of glass. Otherwise, you don't get total internal reflection. So this is in real engineering of a fiber. Okay, they have to put some sort of all sorts of sleeves on top of it, but they have to make sure the sleeves have lower index refraction. Okay, any questions? All right, last part of this chapter is, we already talked about polarization, but we haven't talked about polarization due to reflection. Okay, now what does that mean? Okay, so far we have, we know how a beam of light reacts. It goes in the surface between N1 and N2 indices, and if N1 happens to be less than N2, it bends this way, and we have a relationship between the indices. Let me just call this 1 and 2. And we have a relationship, of course, between the indices and these angles, which is Snell's law. So we already know how they're related. But we also have this reflected beam. If you remember, these two angles are the same. The reflected beam angle is the same as the incoming angle. But now, one thing that you just have to take as granted, because it would be a little bit too complicated to prove, is that just take it as granted that if polarization of incoming beam or ray is random. So remember, if the beam is randomly polarized here, if it's everywhere, the incoming beam, then, then at a particular angle, which we'll talk about in a second, the reflected beam is completely polarized parallel to interface surface. Now, that's a lot of words, but let me explain to you. So the incoming beam is not polarized. So I'm showing it with that blue rays in all directions because it's not polarized. So they're all over the place. upon reflection at a particular angle, okay, a very particular angle, okay, the beam, reflected beam, is polarized completely, in this case, out of the page or inside the page. I'm just going to show the out of the page. This is the polarization, completely polarized parallel to the interface surface. Okay, and what is that particular angle? When theta 1 plus theta 2 is equal to 90 degrees. Now, let me call this theta 1, maybe too many notations. Theta reflection. So when theta 1, which is reflection, plus theta 2 is equal to 90 degrees. In other words, when this is 90 degrees, when this is 90 degrees, same thing. When that's 90 degrees, the reflected beam is completely polarized parallel to the plane, or normal to this plane that defines the three beams. Okay? Okay, that's called Brewster's angle. So reflected plus is 90 degrees. So if we were to then all right, so N2, N1, okay? This is N2 greater than N1. So we have the relation N1 sine of theta 1 is equal to N2 sine of theta 2. But we know sine of theta 2 from this relationship on top. Theta 2 is 90 degrees minus theta reflection. But we already know theta reflection is equal to theta 1. So N1 sine of theta 1 is N2 sine of, now of course, sine of 90 minus theta, I don't know how you guys remember, how much you remember this, but sine of A minus B is equal to sine of A cosine of B plus minus sine of A minus sine of A cosine of sine of B cosine of A. Okay. So this will then get us to cosine of theta reflection, but cosine of theta reflection is just cosine of theta 1. And then this will give you sine of theta 1 over cosine of theta 1, which is tangent of theta 1, is equal to N2 over N1. Okay, so this is the angle at which reflected light is completely polarized parallel to plane of interface. So this is the plane of interface between the two materials. And so the polarization would be completely parallel to that plane, where it was completely non-polarized. Okay, so the reflected light, this is it. This is called Bruce's angle, by the way. Okay, so Bruce's angle is the angle at which the reflected light is completely polarized in the fashion I'm drawing here. Any questions? Okay, so only a specific angle. At this very particular angle, you get complete polarization of the reflected light. All right. So we're pretty much done with this chapter. Any questions, guys, before I start the next chapter? All right. So this next chapter is all about images. It's how images are formed, what optical elements do you need to form a simple image, and how you analyze images, and what are images to begin with. So, what is an image? The question is, what is an image? What does an image mean? Well, our eyes will see an object, and that object, then an image of that object is formed inside our eyes, in the retina, and then our brain then processes that and says, oh, okay, so there is an object there. Okay, so the way an image is formed of an object is formed by this thing that I'm going to talk to you about. Here is, say this is an object. Here's an object. Okay, so I have an object. And what happens, let me ask you a question. What happens if this object, of course, say it's illuminated by, here's the sun, and the light of the sun is coming all over the place. And of course, at one of these rays will hit one point on this object, and some other ray hits another point on this object, and so on. But let's talk about this one object, one ray of it here. What happens to that one ray at that one point on my object? What happens to that one ray? What happens to that one ray when it hits that object at that one point? One point on object is receiving one of those rays from the sun. What happens to that ray after it hits that one point on that object? Anyone wants to take a wild guess?
Does it either get absorbed or reflected?
It gets absorbed. Well, definitely gets absorbed, some of it. But then I wouldn't call it reflected unless this object was really, really shiny. But if the object is not very, very shiny, what happens? Well, some of the light goes in like that. Some of it could go like that. Some goes like that. Some goes like that. Some goes like that. Some goes like that. I mean, the light goes all over the place. We call this scattering. So one ray hits one point, and that one point scatters light all over the directions. Unless the object is very, very shiny, metallic, and in which case it reflects like a reflected point. But in usual case, if you look at any object, say I don't know, an orange or a table, these objects are usually not shiny or a pillow or a piece of carpet. Each one point receives a ray, and that one point scatters light in all directions. Okay? Now, let's take two of these rays that are being reflected. Maybe this one was in that direction. Maybe there's another one going in that direction. Okay, so these are only example two of the rays that are being scattered in all directions, two of those rays. We'll get to my eyes. Okay? And then, of course, my eye, in reality, looks sort of like a spherical object inside my head, and there's the retina behind it, and then lens of my eye will bend those two beams and bring them back down somewhere on my retina. So you can see one point on the object was completely mapped onto one point on my retina. And then, of course, there are other beams. Maybe a beam, maybe another sun beam goes in here and produces two other beams in that direction going into my eye. And of course, my eyes will focus it like that into another point. So you can see finally a shape of that object will be formed in here backwards, because as you can see, up goes to down, down goes to up. So there is an image of the object on retina. And this is what an image means. An image is always at one point on the object going to one point on the image plane. That's how you see an actual object. The whole thing is this concept of focusing is getting one point on the object to represent only one point on the image plane. So this is what an image is. An image is point mapping of the outside world onto the retina of your eye to represent what's outside. It's really an image of the outside world. Okay? So one point goes to one point to go another, so everything becomes a one-to-one image of an object world, or the entire field of view becomes a one-to-one image on the retina. That's what an image is. Okay? So that's an image. Your camera does the same thing. Your camera forms an image point by point mapping. When I say point by point mapping, I mean this process that I just drew here. When there's a point-to-point mapping of whatever is outside onto an image plane, like a camera does exactly the same thing, that is called an image. The image is formed by a one-to-one translation of all the beams of light that scatter light from one point and they all gather into another point under the image. This is what an image is. That's the very definition of an image. Okay? Let's do one simple image that we have probably seen in our lifetime. This is a natural image, gets formed. This is called a mirage. Okay, I'm sure you guys, some of you have seen a mirage in a hot summer day, driving down a long highway like Highway 5 that goes from here to LA. And when you look at the very large distance down the road, down the highway, you see this watery looking thing on the road that keeps running away from you. You'll never reach it. That's what a mirage is. So let's find out what a mirage is with all the stuff we have studied so far, because what we are now equipped to explain what a mirage is. All right. Here's the road. Okay, I'm looking at it sideways. And of course, I am in my car like that, sitting here with my head. And of course, my hands are like that. I'm sitting. All right, and the road is hot. Now that's important because you don't see mirages on the road on cold days. All right, so the road is hot because the sun has been shining on it for hours and hours, and it's summertime and it's hot and it's extremely hot. And of course, asphalt is pretty dark color, so it absorbs a lot of the heat and gets really, really hot. All right, so let's look at this small layer of air that is in contact with the road. This is in a small layer of air in contact with the road. Obviously, if it is in contact with the road, it's going to get hot. So this layer of air is hot. Now, the next layer of air on top of the first one is hot, but less hot, because it's farther away from the very hot road. It's only touching the hot air. And as you go up, it's hot, but even less. And finally, of course, this is the temperature of air, which is much cooler than road. So as you go up, temperature goes lower and lower and lower. All right, so far so good. That's not a big deal. It's obvious what's going on. The hot air gets cooler and cooler as you go away until you get to the finally maybe 100 meter away. All right. Now, hot air is less dense. Density goes down when it's hot. That means index of refraction is lower than a denser air. All right, so the index refraction of this air is then lower. Let's say air up here, index refraction is 1.1. And this one is 1.001 because it's hotter, less dense. And then it becomes 1.0, I don't know, 05 or 1.01 and 1.02 and so on. So you can see it eventually gets to this value as you go up. All right, so the index is lower towards the hot road, and then it becomes higher and higher as you go up because the air gets colder and colder and hence denser and denser. All right, let's now look at a beam of light that is starting from here. Let's say a beam starts coming in. Let me put it somewhere else. Let's say a beam of light comes, a beam of light's here, the light source is here. And of course it's coming in straight like that. And let's say this is the uppermost layer that we want to consider for this problem. And of course the index is higher on the top surface, on the top layer, and the index gets lower as it enters this lower layer of air in intensity. So remember what happens? This is theta 1. And when you enter a lower index material, your beam bends away. And then you hit the next layer. And the beam moves away again. And then the next layer, away again, away again. And finally it gets to total internal reflection. And then it goes back this way. And then now it goes to higher, and then it goes this way. And then it goes this way, and it comes back out. So you can see the beam that is coming from the upper, way above the surface of the road at far distance away doesn't travel in a straight line anymore, because as it gets closer to the road, it starts bending away from the road due to this effect that we already know. The Snell's law tells us how these things bend as you go to lower index from higher index. So the beam doesn't go straight, it kind of bends away and finally goes up, which is really weird, but we already know this is true because we know Snell's law. Okay, so guess what happens from a beam? If a beam starts from here, it goes here and goes into my eye. All right, and usually whatever is here, let's say there's a tree or sky or whatever that beam came from, goes to my eye. And now here's the thing. The eye doesn't know that the beam was traveling in not a straight line. The eye looks at this thing and says, whoo, I see the beam of light and the image of a tree and a sky, and it's coming from somewhere along the straight path if I extrapolate down this way. So I see this reflection of something straight by extrapolating straight away from the position. And I see it, if these, of course, these angles are so much smaller the way I'm drawing it, but you see it pretty much on the road, sometimes a little bit below the surface of the road due to this effect I'm just showing you. So this is the reason you see a mirage, because of the Snell's law. And every time light passes through these lower index and lower index layers, it bends towards the away from the road and eventually moves back up. Okay, it's a very small effect, but at large distances, the angles add up, and you see that mirage. All right. Now here it shows you another effect that your brain does. Your brain, when it looks at rays of beam of light, it has no way of knowing that that beam had to travel and bend and all that stuff. Your brain always thinks that beam came straight from the object to you. Your eye plus brain always think that beam of light came directly from the object. Okay, this is important. Directly from the object. It does not know that the beam could have been bent. It does not know the beam was doing all sorts of dances. When it reaches your eye says, this beam must have come straight from the object. So you can see, you can actually cheat yourself or anyone by a mirror or any other object or this mirage that I explained. Your brain and eyes do not know anything other than extrapolating from that straight line. So they always think that the light you're seeing comes directly from an object. So this is actually pretty important. Now we'll talk about it when we get to images formed by flat mirrors and convex and concave mirrors. So, but this thing in red is extremely important to realize. Your eyes always think, of course, in conjunction with your brain, always think that the light comes directly from the object, directly. So in this mirage situation, that blue line is what they think the object, where they think the object is. Your brain thinks the object comes directly, even though the actual beam is doing a curvature travel, as you can see. All right, let me get a screenshot. All right, so we'll get to the rest of this thing tomorrow, and we'll talk about mathematics of image formation with different kinds of mirrors. All right, guys, any questions? All right, then I'll see you tomorrow. Bye.